Hello dear students, welcome back to our YouTube channel. As you know that we are studying about the integral transform, in which we are studying about Laplace transform, and in Laplace transform we have seen the definition of Laplace transform, and we know that we denote Laplace transform by such type of L of f of t, and it is defined as integration from 0 to infinity e raised to minus st f of t dt, correct? After that, we have seen some basic function, Laplace transform of some basic function, and in which we have Laplace transform of 1 which is equal to 1 over s, then Laplace transform of t raised to n, and which is equal to n factorial upon s raised to n plus 1, then Laplace transform of e raised to at, and which is equal to 1 upon s minus a, then Laplace transform of sin at, which is equal to a upon s square plus a square, and the last one we have seen Laplace transform of cos at, which is equal to s upon s square plus a square. We can find also sine, hyperbolic sine at and hyperbolic cos at. Now after that we have seen the basic properties of Laplace transform, in which what we have seen? We have seen about first property, that is linearity property. Correct? We have seen about linearity property. Now we are going to see shifting property. Shifting property, in which we have two shifting property. One is first shifting property, and the second one is second shifting property. Correct? We have seen linearity property in previous lecture. Now we will see shifting property, in which we have two shifting property. First one is first shifting property, and another one is second shifting property. So let's start with the first shifting property. A first shifting property. First shifting property. Correct. Now first shifting property, the statement is as follows. The statement is as follows. If Laplace transform of f of t is equals to f of s, then prove that Laplace transform of e raised to a t f of t is equal to f of s minus a. We have to prove Laplace transform of e raised to at into f of t is equal to f of s minus a. Correct? Now we will see, since we know that proof, since we know that Laplace transform of f of t is equal to integration from 0 to infinity e raised to minus st f of t dt. Correct? And the left hand side of our equation 1, since left hand side is equals to Laplace transform of e raised to at f of t. Correct. So we can write or use this definition here. So we will get integration from 0 to infinity e raised to minus st e raised to at f of t by the definition, since by definition. Correct. Now we can write this expression as integration from 0 to infinity e raised to minus, taking outside, s minus a t f of t dt. Correct. Now we have to put s minus a is equal to p, s minus a is equal to p, and s minus a is equal to p. Then we can write it as integration from 0 to infinity e raised to minus pt f of t dt, and we know that Laplace transform of f of t is equals to integration from 0 to infinity e raised to minus st f of t dt is equals to f of s. Therefore we can write it as capital F of t, and since we know that the value of p is s minus a, so we can write it as Laplace transform of e raised to at f of t is equals to f of s minus a. What the mean of first shifting property? The property is stated that if we have a function f of t and we having multiplied with e raised to at, and if we want to find the Laplace transform of e raised to at f of t, then simply the shifting property says that first of all find the Laplace transform of that f of t, that function, and replace the parameter s by s minus a. If e raised to at, then we can write it as s minus a. If e raised to minus at, then we will write s plus a. Or we can write it as Laplace transform of e raised to minus at f of t is equals to f of s plus a. Correct? And it is the required result. And the general theme of this property is whenever we have function multiplied with e raised to at, and if we want to find the Laplace transform of e raised to at and f of t, then we can directly find the Laplace transform of f of t only, and whenever we get parameter s, we replace that s by s minus a. It is the main theme of this first shifting property. Now by using simple definition of Laplace transform, we can easily find or prove the first shifting property. To prove this first shifting property, we have to learn the definition of Laplace transform first, and we can apply, and some basic substitution can prove the first shifting property. In next lecture we will see the second part of shifting property, that is second shifting property. So stay tuned with us and keep watching our videos to understand each and every theorem or examples based on integral transform. We will continue with the second shifting property. Till then, thank you. Bye.